Hi, so we're back. So last class, what did we do? We talked about easy computer problems. Let me just remind you what class we are. We're talking about the outer limits of reason, okay? And basically we're doing chapter 5. This is the second part of chapter 5, where we're going to talk about hard problems. Last time we talked about easy problems. We talked about addition, multiplication, different ways of sorting things, different ways of searching for things, and Euler's problem about graphs. So today we're going to talk about hard problems. We're going to talk about 5 problems that are very hard, and we'll show you what we mean by hard. Okay, so the first problem is a simple problem. It's called the traveling salesman problem. Sometimes it's called the traveling salesperson problem. Depends how politically correct you are. Okay, but it used to be called the traveling salesman problem. It's about as follows. A person, wants to go, he's a traveling salesman, he wants to sell his wares, okay? He sells widgets or something like that. So he wants to go to a couple of cities. He wants to visit each city exactly once. He wants to stay in each city 3 days, and then go to the next city, and then go to the next city, and then go to the next city, okay? And eventually he wants to come back to the original city that he wants to. But he wants to do it in what's called the minimum amount of flying time, or let's say the cheapest amount, or the shortest distance. Let's talk about the shortest distance. He wants to go through the shortest distance. We can view this as a graph. So he has to go to this city, 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 he has to go to this city. He wants to go to all these different cities. He wants to visit each city exactly once, okay, and come back. So there are a lot of different possibilities. He could go like this. Oops. Okay. He could go like this, or he could go start here and go around like this, and then this, and then this, and then come back there. Or he could go, start here, go around there, go here, go here, go there, go there, etc., etc. Or he could do it with a green pen also. Okay, there's lots of different routes to do it. And what he wants to do is look at a computer, go through each route, see how it's the shortest route possible, okay, what's the shortest distance, and then do that. Now, let's just see how we do it. Okay, this graph has 1, 2, 3, 4, 5 cities. Question: how many possible routes are there for 5 cities? And the answer is as follows. I have 5 possibilities for what my first city will be. Okay, my next possibility is the next possible city. I don't want to visit that city again, so I have 4 possibilities for the next city. I have 3 possibilities for the next city, I have 2 possibilities for the next city, and I have the last city. After I visited the other 5, I only have 1 city left, okay? And so that's 5 times 4 times 3 times 2 times 1, 5 times 4 is 20, times 3 is 60, times 2 is 120 cities. I'm sorry, I have 5 cities that I want to visit. It would take 5 factorial, this is called 5 factorial, which is equal to 120 possible routes. Now, if I'm a computer, what do I have to do? For each one of these 120 possible routes, I have to add up how much it costs to go, how much the distance it is from one city, from the first city to the next city, from that city to the third city, from that city to the fourth city, from that city to the fifth city, and then I want to come back to the original city. So I have to add up all those numbers and keep track how long it took each one of those possible routes, and then find the smallest, the minimal, okay, the shortest amount. Okay? If I had 6 cities, that would take 6 factorial. Okay? 6 factorial is 6 times 120, which is 720, I think. Okay. So that's the way it's done. Very nice. Press pause. Okay, great. Question. So, by the way, if I have 6 cities that I want to visit, it would take, there are 720 possible routes. What I have to do for each one of those 720 possible routes is add up all the lengths, okay? Add up how the distance between each one of those possible, the cities in that possible route, and see which is the shortest. A computer can check about 1,000 routes in a second. Okay, more than 1,000 routes in a second. So a modern computer can do this seconds flat. Okay. Okay, great. Question. How about 10 cities? How long will it take in 10 cities? Okay. How long? I just made a mistake. A computer will take about a million, can check about 1 million routes in a second. How about 10 cities? So if I do 10 cities, what I can do is I can check my calculator and I do 10 factorial, okay? And I get 10 factorial is 36288. 3 million. There's 3 million possible routes. Okay? And a typical modern computer can do that in about 3 seconds flat. No problem. Not an issue. Okay, great. Now, let's say I had n cities. I want to go visit n different cities. Question, how long will it take? Okay? And, before I do that, so that would be n factorial possible routes. Very good. In the book, I give a nice example of this. It's on page 110. Okay, and we have different cities, San Francisco, Chicago, Los Angeles, Miami, New York, Denver. Okay, and I give you the distance between these things. Question, I want to visit each one of these cities. These are the 6 largest cities in the United States. I made that up. Okay, I want to visit each one of these. Question, which route should I take? Should I go San Francisco, then Los Angeles, then Denver, then New York, then Miami, then Chicago, back to San Francisco? Which one should I do? And there's lots of different possibilities. I'd like to know which ones to do. Okay, and again, for 10 cities, you have 3 million. Okay, for n cities, I have n factorial. Question, how long would it take, let's say, for 100 cities? Now, this is not a strange thing, because in 100, let's say you're a traveling salesman, you want to visit the 100 most populous cities in the United States. You want to spend 3 days in each one of them. Okay, so you go from city to city to city to city. You want to do this in the shortest amount of distance, so you're going to drive, you're going to get in your car and you're going to go drive. Okay? It's a typical question, it's a nice question. Okay? And a computer can do this. Just all you have to do is put in the coordinates of 100 cities and do it. You know? And, go through all the possibilities and see how long it will take. Not a hard problem. Okay? It's easy to write the program to do this. All you have to do is go through all possible routes and search for the minimum possible routes. Okay, question. How long will it take, not to go through all these cities, but how long will it take for the computer to calculate what is the shortest possible route? Okay? Well, anybody take a guess on this? Okay? Whenever I teach this in front of a full classroom, I usually never get anything longer than 2 weeks, because we can't imagine a problem that's so hard that demands more than 2 weeks of work. And again, we saw that for 6 factorial, 720, it would take less than a second. For 10 cities, it would take 3. If you do a million routes in a second, it would take about 3 seconds to solve. So I'm asking, how much does 100 cities take? Okay? Well, I worked it all out. It's in the book. It's on page 111. Okay? 100 factorial is equal to, don't move. 100 factorial is equal to, ready? 9, 3, 3, 2, 6, 2, 1, 5, 4, 4, 3, 9, 4, 4. It's on page 111. It goes on for 4 lines. 4 lines. Okay? So it's basically 9 with 157 digits after this. Okay? 157 digits. So it's 9 times 10 to the 157 digits. 157 digits after this. Okay, that's a very long time. But again, I'm not asking how many routes. That's how many routes there are. What I'm asking is a simpler question. How long would it take to go through the routes? Okay, so I do all the calculations, page 110, 111, 112, I do all the calculations, and I go through it. And I can show it to you, but you can look in your own book. Okay, 100 routes, okay, divided by 1,000,000, okay, because I'm not interested in how many routes. If I divide it by 1,000,000, this is how many routes. If I divide it by 1,000,000, this is how many seconds, okay? And then I divide it by how many, there are 60 seconds in a minute, and I get how many minutes. And I divide that by 60, because I'm interested in how long. So 60 minutes, I get how many hours, okay? And if you divide it by how many hours, you divide it by 24, you get how many days, okay? And if you divide days by 365, you get how many years. And just to make it a little bit more interesting, if you divide years by 100, you get how many centuries. How many centuries does it take for your computer to do this? Okay, and we come up with an answer. And here's the answer. 2.9 times 10 to the 147 centuries. That's how long it will take you to figure out what's the best route. I'm sorry, 142 centuries. That's how long it'll take to find out that's how long it'll take to find out what's the best possible route for you to travel through these 100 cities. Okay? 2.9 times 10 to the 142 centuries. Great. That's way longer than 2 weeks. Okay? That is impossible. Let me just tell you, I mean, the world hasn't been around till then. By the time the world, the sun will have a heat death long before that will ever happen. Okay, what that means is that we cannot find the best answer. Now, there's different ways of trying to fix this problem, and we're going to talk about that a little bit later on, but basically, it's a long, long time to solve this problem. And again, I asked a simple question. I could have asked a harder question. What about 300 cities? I want to visit the 300 most populous cities in the United States. How much time does it take? Okay? So this problem is called the traveling salesman problem. And it's a very nice problem. Okay, I just want to say, this is not an abstract thing. For example, we live in Brooklyn. Think of a street corners of Brooklyn as dots on a vertex, dots on a graph, okay? And you're a bus driver, and you want to drop off your students. You have to go to certain particular blocks, and you want to see how long it takes. Okay, you want the shortest possible route to return all your students, okay, to their homes. So this problem shows up where. Any problem? Okay. Okay, great. Let's do another problem. Oh, I'm sorry, hold on. Before we do the problem, this problem, we're going to see all 5 of the problems that we're going to deal with are going to come in 2 different versions. Okay? There's the optimization problem. Optimization problem. Okay? And it also comes in decision problem. Okay? The optimization problem asks, what's the best? I want to know the shortest possible distance. I want to know the cheapest value. Tell me what's the best. Okay? And that's what we just discussed. But there's another way of looking at this, and it's called the decision problem. And it's as follows. You ready? Let's say I ask you the following question. Question. Can I visit these 100 cities in less than 5,000 miles? In other words, is there a short enough route that can do it in less than 5,000 miles? Yes or no? Decision problems always have a yes-no answer. Okay? So I want a yes-no answer to this question. So again, given a graph, okay, and all the weights, and k value, k is an actual number, k is a natural number. Question, can I go through the graph, hit every single city exactly once, come back to the original city in less than k values, in less than k miles? Yes or no? Okay? Let me just give you the distance, let me just give you the, a way of thinking about it. So, let's talk about runners in the United States. I can ask the following question. Who's the fastest runner in the United States? And I can look in some magazines and I can look at some websites and I can find who the fastest runner is. But then I can ask another question. So that's an optimization problem. Who is the fastest runner? Or tell me how fast the fastest runner can go in the United States. But then I can ask another question. Is there any runner in the United States that can do a 2-minute mile? That means run an entire mile in 2 minutes. That's a yes-no answer. Yes, there is somebody. No, there isn't somebody. Now, if you can answer the optimization problem, you can definitely answer the decision problem. Because if you can answer how long it will take you, you can definitely answer if there is one shorter than this or better than this, yes or no. Okay, great. Okay, but I want to look at the decision problem. Now, yes, we're going to talk about the optimization problems a lot, but we're also going to talk about the decision problems, and we're going to see later in part 3 of this chapter that the decision problems are very important. Okay, they show up very much. Okay, but I'd like to go through this problem, the traveling salesman problem, again as a decision problem. Okay, and it goes as follows. It says, given a graph, and we want the graph to be 2 things. One is the graph should be complete. What does that mean? That means you can go from any vertex to any other vertex. Okay? That's called a complete graph. I can go from any vertex to any other vertex. So here I can go this way, I can go this way, I can go this way, I can go this way. This guy, I did these 2, but I can also go this way and this way. And finally this guy I can go there. I can go from any vertex to any other vertex, because when I'm traveling, I don't want to be restricted. I don't want to say, oh, you're in New York, you can't go to Denver. No, you can go from any vertex to any other vertex. Okay? So that's one thing. The other thing is weighted. Weighted means each edge has a number on it, a positive number. Okay? So this is 54, and this is 72, and this is 128, and this is 6, and this is 13, and this is 25, and this is 93, and this is 72, and this is 81, and this is 91, etc., etc. Okay? Each edge has a number on it. The number represents how long it takes, or how many miles is it from one city to the other city, or how many hours flying does it take from one city to the other city, and we're interested in minimizing the amount of flying time. Okay? So that's what we're dealing with. So if you're given a graph that is complete and weighted, and you're given a number k, okay? And you ask the following question. In this graph, where I can go from any city to any other city, and the amounts given are given here with these weights, question, can I make a complete cycle. Cycle again means coming back to the original place. Hitting every city exactly once in k or less time, or k or less miles. That's a decision problem. It's a yes/no answer. Okay? Okay? So let's do it. That's for 5 cities. There's a nice example for 5 cities. Here in the book on page 110 is a nice complete, actually I wrote down these numbers I actually looked up these numbers. This is for 6 cities: Los Angeles, Miami, New York, Denver, Chicago, and San Francisco. I can go from any city to any other city, complete. They're weighted, I put the weights on it, and I'd like to know, can I do it in less than 5,000 miles, yes or no? Okay? And so, again, a decision problem, you're given a complete weighted graph and a number, and you give a yes/no answer. An optimization problem, you're given a complete weighted graph, and you want to know what is the shortest route to do it. Great. Okay. Now let's try another problem. Okay, so this is the first problem. Okay. Let's tell you the second problem. Hamilton Hamilton cycle problem. Okay, Hamilton was a great mathematician. Okay, and it's like the Euler cycle problem, which we saw. We saw the Euler cycle problem last time. Let's just remember how the Euler cycle problem is. You're given a graph. You want to cross every single bridge, edge, line exactly once, and you're going to come back to the original place. Now we're going to deal with something else. The Hamilton problem, you're given a graph. Seen this graph before. Okay? And you want to know as follows. Can I start at some node, hit every node, not hit every edge, hit every node exactly once? Okay? Let's do it. Okay? So this one is pretty simple. And I have to come back to the original place. I have to come back to the original place. I started here and I finished here. Notice I didn't hit these edges. Doesn't bother me. I don't have to hit every edge. I have to hit every node. Okay? Let's do a little bit more complicated one. Okay, can I do this one? Okay. The answer is, I think, yes. Okay, that's good. Okay, great. Let's do it a little bit more complicated. Can I hit every single node exactly once here also? Let's see. I'm going to hit that twice. I'm not allowed to hit that twice. Anyways, I think I can do this one. I think there's no, I was about to write Euler cycle, no Hamiltonian cycle. So here, Hamiltonian cycle, yes. Here, Hamiltonian cycle, yes. Let's do another one. Is there a Hamiltonian cycle here? Okay. Okay, we do this. Anyway, absolutely. Just go around like this and come around like that. No problem. Okay. And how about here? Is there a Hamiltonian cycle here? Okay. And the answer is no. So there's a Hamiltonian cycle here. There's no Hamiltonian cycle here. Let's see if you can see why. Okay. Okay. So there is something called the Hamiltonian path. Okay. Here, you don't necessarily finish at the same place, but you can start and finish in a different place. Remember we talked about this. A cycle starts and finishes at the same place, like a bicycle. You come around and you come back to the original place. A path through the woods. You start one place, you end up someplace else. So, question, is there a Hamiltonian path? Can you hit every single dot exactly once, but you come back not necessarily to the same place? And the answer is yes. Watch. Go around like this. I started here, I finished here, I hit every single dot exactly once. Okay? So this does have a Hamiltonian path. How about this? Well, this has a Hamiltonian cycle. If I just stop right before finishing, now it has a Hamiltonian path. So if it has a Hamiltonian cycle, it definitely has a Hamiltonian path. How about this? I don't know about this. Again, if it has a Hamiltonian cycle, I just stop right before I get to the end, and it'll have a Hamiltonian path. So these two have Hamiltonian paths. How about this? Does it have a Hamiltonian cycle? I think the answer is, I'm sorry, it doesn't have a Hamiltonian cycle, but it might have a Hamiltonian path. Let's do it with a different color. So I'm going to start here, go around here. That's a tough one. I don't see it. I think no Hamiltonian path either. Okay, so some do and some don't. Okay, let's just do one more of this type. I like these. How about this? Like all this lips. Hamiltonian cycle? No. How about a Hamiltonian path? Okay. Anyways, no Hamiltonian cycle, no Hamiltonian path. It doesn't. You could try all you want. It doesn't. Okay. So this is mostly, again, this is the Hamiltonian cycle problem or the Hamiltonian path problem. It goes as follows. Given a graph, tell if there's a path or a cycle, if there's a way of going through each one of the edges, coming back to the original edge, then there's a Hamiltonian cycle. If there's a way of starting at one vertex, let's do that again. Hamiltonian cycle. Given a graph, tell if there's a way of starting at any vertex, any dot, going around visiting every single other vertex exactly once, coming back to the original vertex. If the answer is yes, then there's a Hamiltonian cycle. Okay? If you can do it, but you can't come back to the original thing, then there's what's called a Hamiltonian path. Not a Hamiltonian cycle. And as we saw, just like with Euler, sometimes there's a path, sometimes there's a cycle, sometimes there's neither. Okay? So we have to check. Okay, great. All right. Okay, let's just talk about the optimization problem versus the decision problem. The optimization problem is show me the path. Show me the cycle. Okay? The decision problem is tell me yes or no. There is such a thing or there isn't such a thing. Okay? And now on the test, I could ask you either one. I want to see what the optimization problem is. I want to see what the solution is or just show it to me. Okay, so that's called the Hamiltonian cycle problem. Okay? Great, ready? Now I taught you the trick for Euler cycle problem with the odds and the evens, okay? Look at every vertex and see what you have. How about the trick for this one? Tell me, how do you tell whether or not a graph has an Euler cycle or not? What's the trick? Okay, I'm going to let you try to think of a trick yourself. Okay, I'm going to erase the board, give you a second to think of a trick yourself. Okay, you can try to think about odds and evens, you can try to think about how many vertices it has, etc., etc. You can shut off the computer now and think about it for a little bit and try to come up with your own little trick before I tell you the trick. In fact, it'll be much before. Okay, so, it's okay. Okay, so we're thinking about the problem. What's the trick that tells you quickly if there's an Euler cycle or an Euler path? Now, again, I can give you a graph with about 100 vertices, and I can ask you the question, is there an Euler cycle, is there an Euler path? Okay, ready for the trick? I don't know of any trick. I do not know of any trick. There is no, it's not only I don't know of any trick, no professor knows of any trick at the moment. So, the only way to solve this problem is try all possibilities, which you were doing in your head the whole time. You were going, let's see, no, yeah, this works. You try this, try that, trying all possibilities. Question, how many different possibility paths are there? How many different possibilities? Well, if you have 6 vertices, let's say, okay, so you want to see if you can do an Euler cycle or an Euler path. By the way, this you can, for sure. Somebody just go around like that. That is an Euler cycle, no problem. But what you want to do is, and again, this is not a complete graph. With Traveling Salesman, I needed a complete graph. Here, I'm just giving you a graph. I give you any graph, I want to know if there's an Euler cycle or an Euler path. To make it more interesting, you can do this. Okay? Make sure that there are vertices here. Okay? Does this have an Euler path or Euler cycle? What you have to do is, you have to try all possibilities. Try all possible routes. How many possible routes are there? Well, I can start here, I can start here, I can start here, I can start here, I can start here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. Great. So there's 9 potential starting places. Now, once I start someplace, I have 8 other possibilities to go. And then once I do those, since I'm not visiting any vertex more than once, I have 7 possibilities after that, and 6 possibilities after that. And 3 times 2 times 1, this is 9 factorial possibilities. Great. That's for 9 vertices. What happens if I give you 100 vertices? Well, that's 100 factorial. Okay? And you have to try all 100 factorial possibilities. I showed you how long that would take. What do you have to do? For each possible route, you have to go and see, is this vertex connected to that vertex? Is there an edge between those 2 vertices? Is there an edge between those 2 vertices? Is there an edge between those vertices? If there's an edge between all of them, and then there's an edge going back home, yippee, then your answer is yes. Otherwise, you have to try the next possible route, and the next, and the next. Okay, great. For 100 things, this will take 2.9 times 10 to the 142 centuries. That's a long time. It's a long time. That's a very long time. Okay, great. Let's go to the next problem. So the Hamiltonian cycle problem is also what's called an n factorial problem. It takes n factorial to potentially solve this problem. Okay, let's do another one. Okay. The next problem is called the set partition problem. The set partition problem is as follows. I have a group of students. Each student has an age. I want to split the students so that they have the same ages all together. In other words, I want to split them so that if I add up all the ages in this set, it'll be the same as adding up all the ages in that set. Okay, question, can I do it? Okay, so let's do it. Let's do a typical example. 5, 13, 8, 17, 21, 23. Okay. Can I split these numbers into two sets such that when I add them all up, I get whatever? Okay. Now let's just go through this. Okay. You can try to do it yourself. Again, I want to put some numbers in here. I'm splitting this set into two sets. Some numbers in here and some numbers in there, such that when I add them all up, I'll get the same thing. Okay. Now, the answer is, for this set, the answer is no. I'd like to show you why. Because if I add up all these numbers, I will get an odd number. I don't know what the odd number I will get, but I can tell you very quickly I'll get the odd number. Let me show you why. Because there's one odd number here, an odd number here, an odd number here, an odd number here, an odd number here. So I have 1, 2, 3, 4, 5, 6 numbers. 5 of them are odd numbers. When you add an odd number and an odd number, you get an even number. But when you have an odd number of odd numbers, like we have here, then you have an odd number. So if I added up all these numbers, I would get an odd number. Now, let's just add them up and get it. 5 plus, let's do it with a calculator because it's easier. 5 plus 13 plus 8 plus 17 plus 21 plus 23 is 87. Okay? 87. So if I wanted to get such that half of those numbers would be here and half of them would be here, okay, then I would need 43.5 in here and 43.5 in here. No way in the world we can do it. Okay? So, the answer to this problem, can I split the set such that the sum of all these guys is equal to the sum of all these guys? The answer is no. But let's change the problem. Let's make this from a 5 to a 4. Okay? Now let's see what happens. Now I have 1 odd, 2 odds, 3 odds, 4 odds. If you add 4 odd numbers plus 2 even numbers, you're going to get an even number. Okay, that was a 5 divided by 4. I just subtracted 1. That's 80, not 87, but 86. 86 divided by 2 is 43. Question: can I get 43 in here and 43? Okay, I don't know the answer. So as far as I can see, I can't get 43 out of here. But if I change this to 0, okay, then let's just see, I have 1 odd, 2 odd, 3 odd, that's an odd number. Oh, so then I'm not looking for 43 anymore. Anyways, it's an odd number, so for sure I can't do it. Okay, so, but I can change this back to a 5. Okay, so I subtract the 1, so now this is again 86, let's just do that. This is 43 plus 5 is 48, 56. Oops. Anyways, I think here I can do that. Okay, so here let's just go through this. I have 1 odd, 2 odd, 3 odd, 4 odd. So 4 odds is an even. Okay, so this, let's just go through this. This is 43. This is 15. I'm sorry, 25. Okay, and that's 18. Okay, 43, 25 is 8. Okay, ready? I can put 20 and 23 over here, and I can do 5 and 13 and 8 and 17 over here, and we do it. Okay, let's just make sure. This is 30 and 13 is 43. Okay, so we did it. Notice, they don't have to have the same numbers. I don't mind the same amount of numbers. This says 2 guys, this says 4 guys. That doesn't bother me. Okay, the point is, can we partition, split, not in half, but split, such that all the numbers in this guy's set have all the numbers. It's the same amount as all the numbers in that set. Okay. I'm embarrassed to do another problem because I'm not very good at these problems and I can't find it. Okay, great. Let's go through it as a decision problem. Let's go through it as a decision problem. Let's go through it as an optimization problem. An optimization problem is, tell me, can you do it? Yes or, tell me what do I put in this set, what do I put in that set? Okay, and that will give me the answer. As a decision problem, I just want a yes-no answer. Now, I told you how to find a quick way of saying no. Let's go through that. If I give you a bunch of numbers, okay? If I give you a bunch of numbers, and when you add up those numbers, if I give you a bunch of numbers, and when you add up those numbers, you see, oh, all the numbers when you add them up are odd, you know for a fact you can't split them. We're only dealing with whole numbers, we're not dealing with fractions. You can't split an odd number. Okay? So for sure the answer is no there. But I can give you a set with only even numbers, the sum is all even, and still the answer will be no. For example, 34, 6, and 8. Let's do 4 also. Here's all even numbers. Okay? But there's no way in the world you're going to get 2 sets. Okay, let's just go through it. 34 plus 6 is 40, 48, 52. This is 52. So we want 26 in each. There's no way in the world you're going to get 26 in each, because you have a 34 here. So, again, if I give you a bunch of numbers and you see how many odd numbers, you have an odd number of odd numbers, you know for sure that the sum is odd, and there's no way in the world you're going to split them up. However, that's a quick way of saying no, but you might still have evens, which will give you a potential yes, and still you can't do it. The example I gave before was another example in which you cannot do it. Great. How much work, how long will it take for a computer to do this? First of all, how would a computer do this? Okay? A computer would do it very simple. It would take a bunch of numbers. Let's put in some more numbers here. 5, 13. Maybe this one can be done, maybe it can't be done. The computer will go through a bunch of numbers, okay, and go through all the possible subsets of this number, of this set, and see, okay, here's a subset, how many numbers, add up all these numbers, here's all the things not in the subset, okay? Question, if all the things in the subset is equal to all the things out of the subset, then you have a good set. You've partitioned it. You've successfully partitioned. Here's what's in the subset. Here's what's not in the subset. You got it. Question. By the way, a computer can do that very easy. All it does is take a bunch of numbers, add them up, look at all the numbers not in the subset, add them up, see if these two numbers are equal. If yes, whoopee, we won. If not, try again. Try another subset. Try another subset. Try another subset. Okay. Question, how long will it take? Well, how many subsets do you have? So if you have 1, 2, 3, 4, 5, 6 elements, how many possible subsets do you have? We know that. It's 2 to the 6. Okay? We did this in the first part of the class. Okay? Remember, if you have a set that has n elements, if S has n elements, then the power set of S has 2 to the n elements. Okay? So if this set has 6 elements, you want to look at all possible subsets and see if the 2 to the 6 is 64. 64. Not so hard. Okay? Great. Let's say I give you a set with 100 elements. How long will it take? So I can look at 2 to the 100. Okay. I work it out in the book how long it'll take. And the answer is, ready? 401 trillion years. I'm sorry, centuries. Now 401 trillion centuries is not as bad as 2.9 times 10 to the 142 centuries, but it's still a long, long time. Good stuff. Okay, it'll take 401 trillion centuries. I worked this all out. Okay, unanswerable. Essentially unanswerable. Great. Okay, now we're going to go through next class. We're going to finish up all the hard problems. I just want to tell you there's 2 other hard problems. One is called the subset sum problem. Which is very much like this, a little bit of difference. And the other thing is called satisfiability problem. Satisfiability problem is about logic. Okay, so we're going to go through that. It'll take us a little bit of time because we're going to learn how to do truth tables with logic. Okay, so that takes care of that. Let's just go through what we did today. We talked about 3 hard problems. The traveling salesman problem, the Hamiltonian cycle problem, the set partition problem. Okay, and we saw that each one of these 3 hard problems is extremely hard to find a solution. It's very hard to find a solution, and it would take trillions of years to find a solution. This is in contrast to the previous problems which we did in the last things, which takes seconds flat, microseconds flat. Okay, so we're going to finish up the hard problems next time. Take care.